Okay, let's begin our lecture on PDE. Hopefully, this is our last chapter. This is chapter number 4. I'll start from the chapter 4 and we can finalize the things later if we got some times. Okay, so the chapter number 4, it's about the method of separation of variable. So it is not new for you, I guess, because we have already study about the separation of variable in our elementary differential equation, as well as hopefully you can also know these things in your OD lecture as well. So this simple thing we're going to use to solve, it is kind of a application of partial differential equation. Okay, so this is kind of the special equations which I also already told you, I guess, earlier too. Some heat equations as well as wave equation and also Laplace equation, which we known as mostly we use in our application part of the PDE. As you can see, this also coming under engineering as well as in many, applicational real world situations. Where we can model those things with the since it is depend on many variables, many independent variable, we can have that in a category of these three equations. Okay, so in that sense, we also can be incorporate those with the boundary value problem with these equations. Use also Fourier series techniques. I think you may clearly, you will study this one later also in your integral calculus sections. Maybe I don't know you have started, but maybe in the next semesters. Okay, so I will just using that just to to solve these equations. Okay, that is actually our chapter number 4. So you can also see its heading can be I have allocated from here actually. So far we have studied two. First of all, we have defined all our PDE basic stuffs. Then we also have classified linear, semi-linear, quasi-linear and non-linear cases. And then we also have formed by eliminating arbitrary constants how we can form the partial differential equations. And as well as we also solve first order PD, but Lagrange's, Chapit's method, and all these we have so far we have finished. Okay. Also in our earlier section, we have solved second order linear PDE, which we have chosen a homogeneous equation with constant coefficient as well. Now the last part, which apply these method of separation of variable to solve heat wave and Laplace equation. This is our final part. Okay, so hopefully we have I think this lecture as well as one more lecture. Okay, I will hopefully finish everything within this 2 lectures, and we can have our exams, and that's all about our things. So we almost finished our course. So likewise in our other course, you can also get ready for this course for our semester as well as our unit exams. Okay. All right. So unfortunately, I couldn't get time to type yet. Okay. So I'm going to write it. So you can also write with me. Okay. So actually the heading, you can use this heading for our chapter number 4, which is a method of separation of variable to solve heat wave and Laplace equation. So this is our heading for the chapter number 4. So one by one we can solve it. Please can you write with me, so it will be very easy for me to get the things. Okay. Okay, first of all, we're gonna see the heat equations. So I will use my whiteboard to write. Okay, so now, so first of all, we're gonna solve our heat equations. Mostly in this section, we are not, as you can know, this equation has been defined because we are considering 3-dimensional maybe. Okay, x directions as well as, let's say this one x direction, this y direction and z direction. Okay, in terms of the dimensional also, this equation can be changed. For example, the heat equation, as I said to you in our earlier chapters, the heat equation has the form of da bar u over da bar t, which is equal to, let's say, alpha squared or c squared. In some book they use alpha squared for this one. Okay, alpha squared or c squared maybe. Okay, and also da bar squared u over da bar x squared. Okay, so deriving this equation is some process which we, if you are interested, you can find in some books. Okay, it is not a big thing anyway, but it incorporates like I think in physics or something they may do the derivation. Even in our special courses, I think we have derived this one, but for you it is okay. Okay, heat equation, sorry about that. And so alpha squared, maybe in some book they use c squared, in some book they use kappa. This is one of the constant, okay, heat constant. And also this is actually the equation. So as I think I already told you in one of the chapter, I guess maybe chapter number 1. Okay, so this has the form da bar u when we are, I think when we are classify, I told you. Okay, we can choose anything. For now, let's take alpha squared or c squared, whatever. It is fine. Okay. So if you are, confused, I'll use. Give me a second. So since I'm gonna take so many variables, I better use something c squared or c. Okay. Okay. Let's fix here. So whatever I'm taking, I will take in your exam also. So you don't need to confuse yourself. Okay. So this is, you can see, this is a partial differential equation where the u is a function of x comma t. It means it has a, I mean, if you are considering a 3-dimensional, you can define x, y, z, comma, sorry, comma t. Okay, which depends on three-dimensional, which with respect to t also. Okay, since we in the, as you know, partial differential equation is all about the function of more than one variable, isn't it? So if it is only one variable, okay, for example, if it is only ux, it can come under the differential equation. No? So there is no need to study these things, and I mean PDE is no need. But since in the real world problem, we can't have only one variable because it depends on more than one variable. For example, if you say like what we can say, if you are deriving some equations which is dependent more than one variable, it has the so many laws. If you are, I think you also studied in the physics in A level as well as here also you may study, because we can't derive the equation in one term in always. Okay, because so many real world things uh, involving and deriving one of the equation. Okay, so that's the there we need some PDE needs. Okay, so that's why we are studying PDE as well. In terms with the ODE, we also studying PDE because there are situation comes with where we have to deal with the more than one variable. Okay, so that's that. So here as you can see, I'm gonna as like in your coursework also, because we have studied so many things now, so we have restricted here for you the only the case of one dimension. That means I'm going to have only the x direction. Okay, x directions. So if you if you are interested, or in, I think in special courses, we also incorporate this one with let's say if it is two dimensional in the sense we are only considering the space. So x, y is a space, no? Did you understand? If it is x direction, only we are considering the one line. I mean the real line. Okay. If it is as like, I think I already told you these things in the vector space as well. If it is xy coordinates, okay, it is a two-dimensional, isn't it? So if you are considering three-dimensional, it is like kind of a three-dimension. It's like a, for example, let's say box. okay, kind of a cube kind of things we can have under the three-dimensional. So if you are having something like in a two-dimensional, you can have some, let's say, I mean, what we can say, like for example, circle. Okay, it is also coming under XY things. Okay, so I hope you understand something. There's a if it is one-dimensional rod, you know the rod, no? Like for example, if you are heating a rod, or what you can say, for example, if you are heating one spoon, let's say spoon kind of things, okay, it is kind of a one dimension. If you are if it is going further spaces, further dimensional things, it will go under here. But for some reasons, we are restricting our studies only for one dimension. So I'm just introducing what if you are having two-dimensional. Okay, this thing already there. This is only depend on t, no? Time is okay. So what if you are having, let's say, in terms of two-dimensional? So I can consider x term and y term. So hope you can understand the third three dimensions, isn't it? So x term as well as y term and z. So as you can say, this is a two-dimensional case. I mean, order two. Okay. So since the heat equation coming under the order two, so it is I mean continuation of the chapter 3 to chapter 4. Okay. All right. So that's just the introduction. I will go for the solution part. Okay. Okay, so if you consider only the I mean one-dimensional heat equation, for example, I can show you in a I mean graphical way. Let's say I'm heating one of the rod, okay, maybe the iron rod, okay. So if I heated this one in this side, it will be 0 to L. This is my length of my length is depend on, okay. Also there are according to, for example, if I heat the iron rod, or maybe I can heat the plastic rod, okay, plastic, or if I can wood rod, okay, wood spoon or anything, okay, or aluminum. So these kind of things also depend on, no. So these are that alpha square, as I said, alpha square or c square, which is depend on these things, okay, according to the I mean the material we are used, that is happening there, that is we all derived as a constant. So when you see, if you are interested, you go for and find out in this time period, you can find the derivation of the, so this is your homework kind of, reference. Okay. Sorry. So derivation of one diamond. If you are interested, you can go for it. Okay. How this equation has been derived. Okay. That is a little bit of, I mean, sorry about this. If you are interested, you can go through. So I think it will come under physics also. So I hope you can, it will be very interesting. So you can go for it. Okay. Okay. Now the thing is, uh, we are going to solve this one. Okay. When solving comes, we have to give some extra, I mean, conditions to solve it. We can't solve just like that. Okay. So that we call the boundary conditions. Boundary conditions. Boundary conditions, as I can say, which I can abbreviate it as BC. Okay. Also, it is also coming as initial conditions. Okay. So I can abbreviate it as IC. So likewise, how I can compare this with your ODE is, I don't know, you may also have that things, okay? In the ODE case, if you have something, let's say y dash is equal, let's say y is equal to c or something. Okay, this is one of my let's say ODE equation of first order or second order, anything, okay? So in this case, you should have some initial condition, no? So y of 0 is equal to 2 or something. So there we use some initial condition to get our finalized answer, isn't it? To get rid of the integral constant, you may need some initial condition, isn't it? So in that way, okay, if we actually need to get our finalized answer, we should incorporate here involving, since it is also depend on time as well as the space, okay. So here I told you my x is you say x comma t, since I am taking only one dimension. Okay, otherwise x comma y comma something like that. Okay, so if I take u x comma t, see, this is also a space also considering, time also considering. So I need two or more conditions to get my finalized answer. Okay, that's what we are taking boundary condition as well as initial conditions. Boundary condition in the sense, okay, so what is the point here? What is the point here? Okay, what is the heat here? What is the heat here? Like that. Okay, initial condition means at first what was the heat? Okay, before heating, time goes, when we are heating, it will be increase the temperature, no, inside the rod. So before that, what it was? For example, let's say it is in the atmospheric environment. So say maybe something T is equal to 32 degrees Celsius or something, no? So that is that kind of. Okay. All right. So the actually your questions maybe okay. So when we do the example, we can say, I think I'm not gonna do today, maybe in the next class. Okay. So when we are giving different equation, I mean the questions, but the thing this one is same. Okay. Maybe they can give the condition. I mean this constant. Maybe for example, da bar u over da bar t times 4 da bar squared u over da bar x squared is maybe the equation. Okay, for example. So the boundary condition here, I'm gonna give you like a general term here, but according the question, maybe it can be different. Boundary condition is this one, or initial condition this one. Sometimes they may give you in the, I mean, you can see the past paper. They may give you in the like this simpler form, or otherwise they may give you some, like you to derive from the sentences they give. Okay, they may give in a sentence to explain it, you have to derive in a mathematical form. All right, so that's how it is going to be work. Okay, let me continue the things. Okay, hope you just write down something what I have told you. Okay, so just a rough idea, you can write something. Okay, we are not yet going to the solution part. I'm just explaining what can be. Okay. All right. So shall I continue? Okay. Let me give. So everyone joined already? Okay. Now let's continue. So this is actually the form of, I'm writing again. Okay. Da bar u da bar t. Let's say, okay, c squared. Okay. Da bar squared u. Sometimes you may get alpha squared. I already told you. Okay. So let's say my boundary condition. Now I'm going to use this abbreviation. Okay. At 0 comma, I mean, at now in the boundary condition, you can, see the only thing is going to change is this one. Actually, our equation u is depend on x comma t now. So here in this boundary condition, it's depend on the space. Okay, space only gonna change. So let's say at the zeroth space, okay, I mean, I told you I'm going to take the rod as 0 comma L, okay, maybe smaller, okay. So this is my initial point. This is my ending point in the rod, in the space, okay. So what if it is 0 point, I'm for the easiness, okay, to derive the general equation, I'm going to have 0. Similarly also, for the easiness, I'm going to take L comma T. Okay, so this may be different in your examples. Okay, according to the example, you can incorporate the way of solving. Okay, so this you can see this is only changing. This is not a vector. This is only changing. Okay, similarly, initial condition in the sense it will be depend on the time. Okay, so initial time. So it means initial time is what? 0, no? Yes, u of 0 comma, it can be anything. Okay, so initially the space can be anything, but at the time is equal to 0, I have, let's say for example, a function of x. Since this is only depend on x, no, so I'm gonna take something. Okay, but for the example they may give some, for example, sine x or e to the power x, something like they will give you. Okay, So according to the question, you have to deal with that. Okay. So now let's get into the solving process. Okay. It may be simple for you. It's not that much harder, I guess, because you're already in the contact with the OD, So actually, the separational variable is coming because we are finding some difficulties in the PDE solving two-dimensional this kind of application. Okay, what we are doing is using the separation of variable, we are finding two ODE case. Okay, we are just transforming the PD into two ODEs. Okay, then ODE is fine now. It is only depend on one variable. So we can solve that two ODEs, and then we are incorporate the answers. Okay, that's what the procedure. All right. So let me first of all write the solution method. Let, okay, x comma t, I'm gonna have for the easiness, okay, to get the separational variable. So I'm gonna have this one can be xx and t of t. Okay. So ux comma t, I am taking as a function xx times tt. Okay. So x is one of the function which depend on x. T is one of the function with respect to t. Okay. So these two are, yeah, separationally two functions has been multiplied. It is my partial differential equation. Okay. Why I'm taking? Because to get our separational variable. Okay. This is a process. Anyway, this is how you have to solve it. Okay. So, all right. So let me, first of all, let's incorporate my boundary conditions. Okay. As I know, my 0 comma t is equal to what? 0 no. So if you put that one, okay, what I'm doing here, x equal to 0 no. My first is the boundary condition, x equal to 0. So I think I can write here, x equal to 0 case, okay. Yeah, u 0 comma t. So if you put x equal to 0, what do you get? X comma 0 and t doesn't change now. This will be 0 for all t. Okay, for all t, I'm just putting my boundary conditions. T doesn't change, only I'm changing my x. Okay, so what you can say, if you have, let's say x equals 0, t is t, which is equal to 0. What do you think about x of 0? Any idea? So a function which depend on zeros. It should be 0, no? Since if you say solve this one, why? Because I'm taking t is not equal to 0, no? T is not equal to 0 because it depends on t. Okay, so this is the idea. Okay, so from this one of the boundary condition, I have took the idea x of 0 is equal to 0. Okay, hope you all are writing with me. Okay. Okay, now what is the case? X equal to L. Okay, in that time, so u L comma t. Okay, I'm gonna put my L tt, which is equal to 0 as well, isn't it? That's what I gave you as a boundary condition. You can see in this boundary condition, yeah, u L comma t is equal to also 0 now. So I have written everything same. It means u 0 comma t also 0, u L comma t also 0. I hope you know these things. Okay. Okay, now, okay, so what in this case, what do you think, Excel? Again, if you say tt not equal, because we are taking this is depend on t. So I'm having Excel also t. So we are not going to use this one now. We'll use later. Okay, let's just analyze using our boundary conditions. All right. So please write down these things. Okay, let me continue. So since I'm having u x comma t, which is equal to xx, I'm gonna take it again. Okay, what do you think Okay, I'm gonna omit for now. Okay, dabba u over dabba t, small t, because this is depend on t. No, what do you think? So if you are, let's say this is my equation number, let's say star. Okay, the star has been partially differentiate with respect to t. So this is not depend on t, no. So in partial differential equation, what we do? So for example, u is equal to x squared t squared. Okay. So what do you do? Da bar u over da bar t. You don't care this one because we are treating it as a constant. So only thing is you have to consider this one as 2t, no? Yes. Okay. So if I say commonly, I can say this is xx is something there, t dash of t. I'm gonna abbreviate it as a t dash. Okay. Okay. So and then okay. How about daba u over daba x? So I don't want to use again. I'm gonna take it directly to the since I'm just abbreviating now. So one differentiation I'm gonna take t dash. So if I take 2 times of with respect to I mean x, okay, you can check again, but it's not a big problem, okay. But what I'm gonna get is 2 times x dash of x. The t doesn't have anything. It does treat as a since we are taking partial differential with respect to x, I can treat this as a constant, okay. So this is what we are having. Uh, yeah. So please put this our main equation. Okay, this equation as 1. Okay, this equation as the equation number 1. So see here, dabba u over dabba t there, c squared there. This one also dabba squared u over dabba x. So we can substitute that one. No? So that's what I am taking. Equation number 1. Please put that equation number 1. Okay, give me a second. Okay, now yeah. So after this one, okay, I'm gonna have another. So using equation number 1, I can substitute this. What I substitute is x comma t dash because for the easiness, I'm omitting that x t and all. Okay, so no need now. I'm just had it earlier because to give you some ideas. Okay, c squared x double dash t. Am I right? For the dabba u or dabba t, I put this one, c squared, this one, this one. Okay. So for the easiness, I'm omitting that x t terms. Okay. All right. Now, what do you think? This is coming under something no. See here, this side x is there, t dash is there. This side c squared there, x double dash there, t there. So you can take all the t one side, x one side, and have some separational thing no. So let's see. T dash. And for the some purposes, I'm going to take c squared also this side. Okay. So let's keep our x terms this side. Okay. So this is our separation of variable concept now. So I have taken all the t terms one side, x term one side. So this is what I am looking for the process. Okay. Okay. Now, what do you think if, for example, we have u is a x comma t. It depends on 2 variables. Okay. But I have separated it into 2. But how come it can be separated? If it is wanted to separate, both should be somewhere equal. They say they have separated t, t function as well as x function. So how can it can be equal? There is no way, no, because t function and x function is nowhere to equal. But if you wanted to equal, you should say both should be equal to some, let's say k. K is a where k is a constant. Okay, what they are saying is, for example, let's say my t function is t squared minus 2t, whatever, okay, which is equal to, let's say, k. Okay, so if I have, let's say, x minus 2x something, also function also, if you wanted to have this also is equal to this one, it also something k, no? Then only I can say this function and this function can be equal. Okay, let's say anything. Okay, so did you understand? So two different variable function to have as a equal, we should have somewhere some point which is incorporate both. Okay, that's we are taking as one of the constant. So it also applicable in the differential equation concept. Okay, partial and differential. So where we are taking this k as a constant, so we can equate both. Okay, so this is very important. Okay. But okay, give me a second. Okay, but the solutions, so we're gonna process more, no? So when you are process more, okay, give me a second. So if you're processing more, you have to deal this k. Okay, depending on the k, the equation has been differ. Okay, so there are three cases we're gonna analyze. Okay, what if k is equal to 0? What if k is equal to negative value? What if it is a positive value? In that sense, we're gonna find out our finalized solution. Okay, that is our process. Okay, let me continue. After that, we're gonna analyze this k in terms of three cases. Okay. Okay, now case number 1. Okay, what if k is a positive number? Yeah, positive. Okay. So positive in the sense to deal with as a in our, I mean, okay, for the differential equations. Okay, so we are going to have k is as a, let's say, lambda square. So for a purpose we are taking. Okay, why we is that correct? Because k is greater than 0. So any squared will be greater than 0, no? Is that any the sense? For example, let's say lambda is equal to 0. 0 squared also greater than 0. Let's say lambda is equal to minus 1. Okay, what is lambda squared? Minus 1 squared is equal to 1, no? That is also greater than 0. What if it is 2? Then lambda squared is equal to 2 squared. This is also 4, greater than 0. Okay, whatever you take as a squared, it will be give us a greater than 0 sense. So I can choose as a any squared. Okay, for the k which greater than 0, I can choose one of the squared term. Okay, so what is our equation? Okay, give me a second. I can write this equation of 2. Okay, please put this as a 2. So we can use that number rather than writing again. Why we are numbering is to use it again without writing again. We can use this number. Okay, which will be simple. Okay, so this equation which I am equating this as a constant, I'm taking as a 2. Okay, so in here, number 2 equation, first of all, I'm going to deal with my this term, x double dash minus, so correct? Sorry, x double dash x equal to k, no? Wherever k, I'm going to put lambda square. Okay, so see here, lambda square, okay, lambda square x equal to 0. Is that correct? I'm cross product and taking this side, which is equal to 0. Okay. What do you think? What kind of equation this one? Please answer me. What do you think of this kind of equation? You have already known this one, no? You are already studying these steps. You know how to solve this, isn't it? Please answer me. I'm expecting your answers. You are very familiar with this in your one of the course, which is parallelly going on. So something like y double dash minus lambda square y is equal to 0. Yes, ODE, isn't it? Linear or anything, ODE. Second order ODE. Okay, you know how to solve this one now? So how to solve this? We say d squared minus, d. We take the like this d squared. Like I'm not using here. Okay, you know how to do that. Okay, d squared minus lambda squared x equal to 0, and you know what is m is equal to plus or minus lambda, something like that. No, so I'm not gonna teach you ODE here, but I'm gonna use your knowledge here. Okay, so only thing is you have to answer me because you all are familiar than me. Okay. So, what do you think? What will be the from this? What do you think? What will be the answer? So that's what I told you. Okay, from the PDE. Okay, sorry, PDE using the separational method. What I have did is I have. So this is one of the equation, one of the ODE case. Okay, and also the T equation also one of the ODE. So I'm just dividing two ODEs. Okay, two ODEs in terms of x and T. Okay, x and T equation of ODE. Okay, did you understand that? Okay, what do you think the x's finalized answer for if you get like this two-dimensional, two second order ODE? So can you solve this using your ODE knowledge? Can you answer me the final answer? You can use any A is equal A and B constants. So t squared minus lambda squared m is equal to 0. Then m will be plus or minus lambda, no? Then that's the answer. You have studied this one in the ODE, no? Second order solving method. Mm, okay, only one person answered. Where's the others? You are in touch with the other ODE part, no? So ODE part, if you help me, it will be good. So I can't teach you ODE also here, no? What is the P actually? Why you use P? Okay, maybe you are familiar with the P, no? So tell me the answer for this. So I don't want to waste my time, so you can go back and see the answer. So lambda x and e to the power minus lambda x. So there are two solutions. Okay. So plus or minus lambda. So I have one of the lambda for the e to the power lambda x and b of the minus lambda x. Go back and study these things. Okay. This is your reference from your ODE section. Okay, so let me continue. Okay, so I can take this yeah, number 3 if I want. Okay, let me continue. Okay, I can't wait for your answers. So I have got my 3 equation which gives x of x is equal to, so I can write x as a x of x. Okay, a e to the power lambda x plus b, you can choose anything. Okay, any constant, a1 a2 anything. Okay, so in this, to get a and b is unknown, no? So we have to find it. Okay, in that sense I can use my, what is the condition which involves space. So there are 2 conditions now, boundary condition as well as initial condition. I told you this is for the which u x comma t, which for which. Okay, which for a space, which for time. I already explained you correct. I have explained much, so can you answer me which one in boundary or initial to get rid of this a and b, which can be useful? Why nobody answering? Everyone here, like 53 people. What's wrong? Only one answering again. What about others? So please don't play around, okay? It will be only ruin your life. So if you are active only, active learning, and if you are answering, or at least actively participate only, you can face the exams. Otherwise it will be very much hard for you. Okay. Anyway, so it can be boundary conditions. Okay. Space is for the boundary conditions. So where if I choose x equal to 0, I will have x0 that I have already found. No, I'll show you where I have showed that. See here. At first I told you this one. X equal to 0, XL is, because to use later I have already derived this. Okay. So you can number it yourself, or anyway, you can use it. Okay. So that's why I have already found. So x of 0 is equal to 0. XL0 also 0 according to what I have defined here for the general case. Okay. According to your question, it may differ. Okay. So I'm going to use that thing here. So if I put a is x equal to 0 for this case, what I'll get? A e to the power 0 now. What the e to the power 0? E to the power 0? Yes. Whatever the, even you put for 1000 0 also 1. E to the power 0 also 1. Any of 0 will be 1, isn't it? So I can say this is 1 plus b also 1. Okay. So this is equal to 0 now from the, so you can write x of 0 is equal to 0. We have derived from the boundary condition. Okay. So if I say, okay, I have the answer a is equal to b is equal to 0. Okay, I can't do anything now. I'll keep it. Okay. Let's say a is equal to minus b. Okay. All right. So what about x? Okay, I'll use another color. Yeah. X equal to L. If you put x equal to L, okay. So so that is all come now. Lambda L plus b of e to the power minus lambda L also. So what is actually we have found there? X of L will be 0 also now. Go back and see. Okay. X of L is equal to 0. So now if I put, okay, what I'm going to do is I'm going to use this to here. Okay. For the b, I'm going to take. So e to the, a e to the power lambda L. For the b, I'm going to use minus a. Okay. So b is equal to minus a now. If I take minus this side. So minus a e to the power minus lambda L, which is equal to 0. This means if I take the a common, I have lambda L minus e to the power minus lambda L. Okay. Which is equal to 0. Am I correct? I'm just taking the a outside. So I'm going to write here. Okay. Shall I continue? Please write down. the steps? So I can continue here, I guess. Okay. I'll use another color if you want. Okay. So what do you think? A times, okay, A e to the power lambda L minus e to the power minus lambda L, which is equal to 0. What do you think about A? Any ideas? What about A? Yes, I got one answer, correct. I'm saying A is equal to 0. How comes? Since I can't, the exponential terms can't be 0, no? Am I right? So x of 0 will be somewhere 1. Okay, it goes like this, no? So 1 to infinity. Or otherwise, it will be only reach, if it is minus now, it will be reach, sorry, 1 to, it will reach 1, but it won't be 0 in any case. Okay, so this is the idea of exponential x now. So we have to have, since you have to tell e to the power lambda L minus e to the power minus lambda L not equal to 0. Therefore, I am taking A is equal to 0. Okay. But now see here, if A is equal to 0, what happened to the B? B is equal to minus A, no? So I can say B is also 0. Please write down correctly. I'm just writing here and there. But I hope you are writing in a proper way. Okay? Okay, I'll go for the next window if you like. Okay, see here this equation. I have this is my answer, no? Okay, give me a second. So this is actually my answer from these equations. I'm saying x equal to a is the lambda x, b, then only I'm using my boundary condition to solve it. Where I have found a also 0, b also 0. So what is my xx? Totally xx equal to 0, no? The thing is, okay, I'll use the other window, okay? See here, if you get xx equal to 0 in any point, there is no point of, solving this equation, no? Did you understand? So I have got x equal to 0. So how come it worked on this process? So ux comma t, I'm having xx and tt. Okay. So if it is 0, totally my answer will be 0, no? So I am expecting something related to this kind. But if I get u is equal to 0, this is not a proper answer. So that's what we call, therefore, which is a trivial solutions. I don't know you have heard this in your OD. Okay, trivial solution means it's not the solution. Okay, so trivial solution in the sense I can, therefore k greater than 0 can be omitted. No, it's not the possible one. Okay, so what I'm doing is I have taken the k. Okay, I am analyzing which k I need to take. Okay, so I have found out this is not working. Okay, I need to go for this and see whether which k I can possibly take to solve this equation. Okay, okay, good. So let's me continue. So I have found k is equal to k greater than 0 is not a trivial solution, so I can omit it. So I'm going to go for the next selection. Okay, case number 2, where I'm going to choose my k is equal to 0. Okay, then what do you think? Our equation xx over x equal to, okay, give me a second. So it's equal to, k, which is equal to 0. So what will get? Double dash is equal to 0, no? So what will be the answer for this ODE case? If you have, for example, double dash equal to 0, what will be the y? In your ODE, can you use your knowledge of ODE? So you go back and get your ODE notes and see get the answers there. Okay, I need a full answer. What you all doing? I didn't get any answer. Only one answer. Uh, so you are studying in PDE, no? I mean, sorry, ODE, no? All these concepts. Why you are not answering? If you don't answer, it's no point to, teach you these things. I can simply give the things and I can go. I don't need to spend much time here. Okay? So very simple question now. What is this? Y double dash equal to 0. If you integrate one time, okay, what do you get? Y dash is equal to some C. Okay, if you integrate again, y is equal to C again x plus C, no, plus D or something. Am I right? Why you all are not answering? This is a very, very simple question in ODE. So I don't know. So if you all be silent, I will go faster. I don't want to waste my time here. Okay, because I also want to finish. These are ODE. I can't teach ODE and PD in the same time. Okay, you can refer the ODE notes and answer me. Okay, so x x of x, from this I can have my answer ax plus b. For example, I'm taking ax, okay, or cx or dx, whatever you can do. Okay, so I don't wanted to use so many variables, so I'm just taking this second case. This also ax plus b. Okay, these are your reference. I can't do this. Okay, so I'm gonna go a little faster because there's no point for you to waste time, because you all not answering. You are not, I think you are not in the lecture. Only one answering, so I can teach only for her. Okay. Okay. Just get the answers. So it will give you b is equal to 0. It will give you a is equal to 0. That's your choice. Okay. Then this is also coming as a trivial solution. Okay, I can go for the next case. Okay, so I have analyzed two cases which are not have worked out. Okay, so let's see for case number 3, which I would like to take k less than 0. Okay, so therefore I'm going to take k is equal to something, okay, minus lambda square, okay, to have my answer. Because whatever lambda square, it will be greater than 0. So minus comes, it will be anyway less than 0. Okay. So my answer will be coming as, I'm just going to write my answer. You can copy. Okay. So this you can learn your ODE part. Okay. So I'm just going to give you the answer. X of x equal to a cos lambda x B sine lambda. Whoever in the lecture, please write down my answer or take the screenshot. So I don't want to wait for others. Okay. Also, you are not allowed to share your notes to anyone until I'll tell you. So if you put the zeros, it will be cos zeros will be 1. So sine 0 will be 0. So I will have something like a is equal to 0. And then if you put like yeah, so L, you will have since a is equal to 0 already, I can use this one. So B sine lambda L is equal to 0 because in my boundary condition. Okay, which is equal to, I can say sine pi L, which is equal to 0. Since of B, I can't have 0 to have the trivial solutions. Okay, trivial solutions. Sorry, non-trivial. Trivial mean we don't have solution. No? So non-trivial solution, I am choosing B not equal to 0. Therefore, I am taking this one is equal to 0. Okay. So how comes the sine pi L which is equal to 0? So pi L can be, which situation the sine pi L is equal to 0? So in the sine, I mean trigonometric way, you know, wherever the pi comes, isn't it? In pi terms, you will have the sign will be 0. Okay, so I'm choosing n for the integers. Okay, any integers of n pi will be 0. So I'm having L pi. So this is like something like this, sin x equal to 0. So where it is possible, x can be any n pi terms. N belongs to integers. Okay. So I can say my lambda is equal to n pi over L. For this case only, I'm having some non-trivial solution, which have find a is equal to 0, but b is there something not equal to 0, but having lambda is equal to n pi over L. So I have found my possible lambda. Okay. Possible lambda can be any n pi over L. So you know n is a integer, maybe 1, 2, 3, 4, and pi is our 180 degree, and L will be the length of our rod. Okay. Okay. So these things in between cases, these are your references. Okay. You can refer and incorporate this solving method. Okay. Now so I'll go for the things. So please get down these answers. So you can leave some spaces to, fill up later when you understand the concept. So there's nothing new here. Everything you have learned in your ODE, just to include here. Okay, let me continue the things. Actually, what we are doing is, okay, we are finding a way to solve it, isn't it? So in here, you can see actually we are solving this one separately. Okay, so in terms of k, so in terms of k, we have analyzed which k, using the boundary conditions, which k has been solved this x variable case. Okay, so we have found k less than 0 only, we have the non-trivial solutions, so that is a possible one. Okay, so we also have to solve this one also. Okay, then only we can put it in our u. Okay, so I'll go for there. Okay, so now we have found our x of x as a solution of, okay, yeah, actually what is our x of x? So in this case we have found our x of x will be for the b, okay, b sine pi x n pi, okay, l of x. So this is our final answer, because where I have derived is this one. See here, x of x is, this is my answer. I have found my a is equal to 0. Then I can omit this one. So this is the only answer I have got for this xx. Okay, in this case. So now, so this one. Then I'm gonna, this is something like, what is the number? Maybe 3 or 4. Okay, you can number in your following. Okay, now I'm gonna solve my t dash of t, c square t is equal to k. Okay, here we don't have much work. Okay, only thing in the boundary case only you have to analyze more. Okay, so here I can say t dash is equal to k c square t. Since I have found my minus lambda squared for the k, okay, so I can substitute. That is the only non-trivial case I have. So minus lambda squared, c squared already there. You can write a capital C or something, because that is one of the constant. Okay. Okay, now what do you think? T dash plus lambda square c square t, which is equal to 0. This is a first order ODE case, no? So what will be the answer? If you have something y dash plus, let's say py, which is equal to 0. So can you try this answer? So anyway, you want answer, I will write the answer and I'll finish up my work. Okay, so I can get the answer, let's say something C. Okay, because this is C, I better use something, no? Let's say D or something. D. Okay. D e to the power minus lambda squared c squared. Okay, for the yeah, t. Okay. I can also write my actual lambda. Lambda I have found like this, no? N pi over L. Okay. So I can just put like this. N pi over L whole thing squared c squared t. Okay. This is small t. So I have found my xx. You can write this as x tt. Okay. Tt is the function of t, small t. Okay. So this is my 4. This is my maybe 5. Okay. Okay, so I have solved for k less than 0. I have found my xx as well as tt. Okay, so multiplying these two only know our u. So that's what I'm gonna do. Okay. Okay, let me continue, and we have to go a little faster because need to do more things. Okay. So then, since I have u x comma t is as xx and tt, okay, I can incorporate my answer as b sine n pi over L of x, maybe, okay, x. And also for the t, I can say d of anything, e to the power minus, what is that? N squared pi squared over L squared c squared t. Okay. So since I have two, two constant, I can write something like, let's say bn. Okay. Bn sine, okay, b. Sorry. Okay. I can use any e. Okay. E of sine n pi x over L, because these variables are, you can choose anything like b1, b2, something like that. Okay. Mostly it's better to use b2, no? Okay, please change this one b2 so it won't make you any um, confused. Okay, I'm going to take this one as b2, this one as b1. Okay, so you can also change there also. Here also you can take b1. Okay, so that's nothing because just a variable name now. Just because I wanted mostly in the books, so most of the people use bn here according to b1 and b2 commonly, because for example, let's say 2 sine something and 3 e to the power something, so altogether I can write 6, no? 2 times 6, 3 will be 6. So this is only a constant, so I can choose anything related to that bn. Okay, sine n pi x over yeah, x, and e to the power minus n squared pi squared L squared c squared t. Okay, so this is what I have found. But actually, since this n coming, no, n is a actually I have taken as a n is a integer, no? Okay, so if you put 1 2 3 like that up to infinity, okay, there you will have so many answers. Okay, so that therefore we can write the general solution, we can is we can write as a series. Okay, so for example, n is equal to 1 what, n is equal to 2 what, n is equal to 3 what. I told you, I think earlier also, if you have two solution, let's say u1 and u2, okay, alpha u1 plus beta u2 also a solution, no? Like a linear combination also will be a solution. Okay, therefore we can write this as a summation, isn't it? Ui and alpha I, something like that. Alpha 1, alpha 2, if you choose something like that, you can write as a summation of linear combination. You may remember in our vector space course. So therefore, I'm writing my finalized answer as a series of equation. There I can use, for example, so here I can use b1, b2. Here I can use bn. Okay, sorry about that because the variable doesn't matter, but I'm just following the book. Okay, otherwise you will confuse. In the books they have used these kind of things, so I'm just using. Okay, so bn sine, here I can put all the n as a summation. Okay, n is equal to 1 up to infinity, because you have to know, don't put n is equal to 0. Okay, 0 term will be 0 already, because I'm talking about the integer part. Okay, it will start from 1 to infinity. Okay, sine n pi L x e to the power minus n squared pi squared or divided by L squared of c squared t. This is actually my finalized answer. Please write down quickly. So don't worry about this variable. So just change it because you wanted to understand. No? So where I am taking b1, b2 as a b, okay, bn. Where since you have to know this constant also, here you can see alpha 1, alpha 2, something like that. No, so you will have infinity number. So alpha 3, alpha 4. So therefore I am also giving n for this constant also. B1, B2, B3 like that, it going. Okay. So this is kind of the general solution. Okay. So we can also have to, because so far we have used boundary condition only. So still we didn't use the initial condition, no. So there only that what I told you, this Fourier series comes. Okay, so you can study the Fourier series later, but just for in this case, you can I'll show you the way how to do that. Okay, not the full, full explanation, but just idea. Okay, have you written this one? Shall I continue? Right, so I'm gonna continue. Yes. So let me continue just the initial part, initial condition part. Okay. Now consider, because that is also there. No, we have to incorporate the initial condition. Okay, I'll use this one. Now consider the initial condition. Okay. So what is the initial condition actually? So you can go back to the first equation. I think, yeah. Okay, see here. This is our initial condition, isn't it? One of the function f of x. So according to the question, it may come something to solvable. But here we are dealing with the general case, no? So I told you the initial condition is depend on the time. Okay, the time in the sense t is equal to 0. What is the possibility of u, which is the initial condition. So that's what I'm going to use. Okay, so let's use our initial condition. Okay, now using the initial condition u x comma 0. Okay, in this equation, okay, you can give some name for this. Okay, okay, you can name what will be the number? I think last I have 4, no? So I can give this one 5. Altogether, I can give this one as 6. Equation number 6. Okay. Okay, so in the equation number 6, okay, if you substitute t is equal to 0, u x comma 0, which is equal to, see here summation n is equal to 1 up to infinity. Let's say my bn or something, sine n pi over lx, doesn't matter, no, this one. What happened to the exponential? So exponential has only the t part, isn't it? Something t. So if you put this one is equal to 0, what is the answer? E to the power 0 will be 1, no? So it will be vanish. Okay, I'm gonna put here. So which is equal to, from my initial condition, I can write this is equal to 0, no? Sorry, f of x. So some case it can be 0 for in your examples. Okay, so f of x, something a function of x. Okay, all right, so which I can write again as f of x can be written as summation of n is equal to 1 up to infinity bn sine anything n pi x over l here. Okay, so actually the Fourier series is like x to l. Okay, just refer if you are interested, but you will study later. Okay, Fourier series, it is kind of a piecewise, we can analyze it. So what it's better you to only know these results. Okay, what I'm going to do is I'm going to take the limit, integral of f 0 to l. Okay, for this with some extra term n pi x over l. Okay, with dx. So what I'm doing is I'm integrating this entire function. I can write this one as a 7, equation number 7. Okay, so I'm integrating the equation number 7 with respect to the limit 0 to l. The function has been multiplied sine m pi x over l. Okay, so what will happen this side? Still I'll have the 0 to l. Okay, summation will come, n is equal to 1 up to infinity an. Okay, sine n pi x over l is there. Okay, this is what I have as the equation. Sorry, this one come. Okay, this is what my equation number 7. With that, I also multiply this one, no? So I also have to put like sine m pi x over L, okay, and dx, okay. Sorry, this one Bn. So which I can write, okay. So I can take the summation outside and put the, since it is depend on the L, okay. So this has been done. Summation n is equal to 1 up to infinity, okay, 0 to L. So yeah, Bn, okay, 0 to L sine n pi x over L, okay, into sine m pi x over L of dA. So I'm just putting the integral inside the summation, okay. So okay, so what that happening is the variable can be changed, okay, because I'm taking the an outside, okay. So the bn has been changed in, because you will understand this when you are doing what is bn, what is an in a constant or any numbers, it will be understandable. So it will be also changed into, let's say, an, okay. So I'm going to use an for this one, finalize answer. Okay, this is just a concern. It doesn't matter. Can be equal or any other concern may be changed according to the process. Okay. So I hope you can write this equation. Okay, please. Okay, let me write again. So actually what I have done is 0 to L f of x sine m pi x over L, okay, which can be written as summation, okay, summation n is equal to 1 up to infinity an. So integral of 0 to L sine n pi x over L into sine m pi x over L, okay, into dx, okay. So this is where only you are incorporating the Fourier series concept, okay. In the Fourier series concept is, you can try the an, which is equal to, what you will get is, okay. So this can be written as this an, okay. So only thing is in this solution, okay, the finalized solution, I'll show you. Okay, give me a second. Actually, see here, this is our actual answer. I mean, actual, we have solved the, give me a second. Okay, this is our actual solution. Ux comma t summation bn sin n pi. This one. Okay, it is depend on x comma t. No, this is depend on x. This is depend on t. Only thing is why we are using the initial condition to get this one bn. Okay, so that one only we are using. Okay, so where the bn, I mean bn or an, whatever. I don't want to confuse you. Okay, let's bn. Okay, bn can be written as 2 over L. Okay, so this is a Fourier series. So you don't need to know the Fourier series. Just write down this. Okay, fx sine m pi x. Okay, m pi x over L dx. So this is the bn. Okay, so the according to the fx, for example, if I say sine x, you can solve this one. Okay, then you can put it there. What is the equation number 6? You can put for what is bn. Okay, bn, you can put whatever the answer you are getting. If I give them, now we don't know fx, no, it is a general term. Therefore, we are just writing the f of x as it is. Okay. So this is a finalized process of solving the separation of variable of one-dimensional heat equation. So if you go for the two-dimensional, three-dimensional, it will be very big processes. So I'm just omitting for because of this course. Okay, you can learn it later if you are doing any special or in your higher studies, you can learn that thing. Okay, so let me recap this one for a second. So actually we are dealing with one-dimensional heat equations. Okay, 1D. So in that sense, I had told you the one-dimensional heat equation may be defined for a rod. Okay, one-dimensional rod. This the equation has been da bar u over da bar t, which is equal to, this is a concern depend on this which material used. Okay, it doesn't matter. C square, they use C square. Okay, sometime some book you may see da bar t k or kappa. Okay, like this kappa, or sometimes they may use alpha square. Okay, it doesn't matter. So I'm here using C square da bar square u over da bar x square. Also, we have given some boundary condition, initial condition to get our finalized solution. Okay, without that we can't solve, no. Okay, now second, this is my actual things I wanted to solve. This is my equation number 1 for the one-dimensional case. Boundary condition I have chosen here. Both end we are having the the temperature will be 0. So U is actually 0 temperature, no, because we are dealing with the heat. Okay, so what I'm telling is, what is the heat here? What is the heat here? This is actually a analytical solution. Okay, or exact solution. But likewise, in we are studying numerical case, we can also solve this one using numerical. Okay, so that is different case. I think not in our course. Similarly, I also gave you initial condition at time 0. We have a function of x. Okay. Now what I have done is, first of all, I have taken my solution ux comma t is since it is depend on space and time, I'm taking space function, time function multiplied by is my solution. Okay. Then I have put my boundary condition to get what is x of 0, x of L. Okay. Then what I have done is, I have taken so ux comma t is equal to this one, no, xx dt. So I have first of all, since my equation has da bar u over da bar t and da bar squared u over da bar x squared, I have partially differentiate this equation in terms of t as well as 2 times x. Okay, so this is my answer. So I have put it there in my equation number 1. Then I have separated my t variable one side, x1 one side. So if I wanted to separate, I need to have it as a constant. Okay. Then I wanted to analyze which constant I can use. So I have analyzed k greater than 0. I found, using the solving method, I have found this is a trivial solution. It means it's not a solution. It's not giving any solution. Okay. Therefore, I have, so it's a trivial solution. So I go for another choice, k is equal to 0. There I also find again trivial solution. So I'm just omitting this one. So then I go for the next selection, k less than 0. So there I have find my finalized solving ODE. Then I found this one. Then I have used my boundary conditions here to get my A and then B. So since to get the non-trivial solution, I am choosing b not equal 0, but found the lambda in terms of sin n pi is equal to 0, which is equal to n pi over L. Okay, now x is equal to, it has been reduced as to b sin n pi x over L. Okay, also I have solved my other part, t dash over c square t is equal to k. Then I found one answer, which is b e to the power minus 8 coming on in the exponential term t. Okay, then what I do is I put this two solution into my solving solution, and then I found this is my actual final answer. Okay, but I have taken one of the constant bn. Okay, you can stop here because this is our final answer. But if they given you in the example some initial condition, you have to use it, isn't it? So when you are using, so we can find the bn. Okay, because these terms are we know already. Okay, only thing is we don't know is bn. So there only we are using our initial condition. There we are using our Fourier series techniques to derive our finalized answer. Okay. So where you, if you put x equal to 0, t is equal to 0, this term will be vanish. Okay. Only this term will be there. So I am just integrating and finding the Fourier series. So Fourier series is a big, vast area. Okay. I can't explain you here. Only thing is I can tell you this is what. So my Bn will be the final answer. So if you memorize or in any point, if you know this stuff, according to the fx given, you can find these things are won't change. Okay, in any of the question, L maybe, let's say L is equal to 4 have given. Okay, and yeah, these things won't change. Only thing fx, let's say is sin x or e to the power x. If they're given, you have to solve it. It is an integral, no? Integral is not our, it's a A-level thing. For example, sin x. What is sin m pi x over L? This one, 0 to L. So solve this. This is the integration. So you know that technique and you can use it and you can find the finalized answer. Okay. Okay. So hope you all understand this concept. Okay. So it took full hours to explain it. Okay. So really a hard thing to, you know. So I just have it to give you the full idea. Okay, so it's not a problem, but explaining other thing only, it's a problem. It's a time consuming. So I'm gonna give you as a homework reference. Okay, please refer it before comes to the next lecture, because hopefully I'll find some questions to analyze in our next lecture. Okay. Anyway, if, to solve this question, because I'm gonna take this chapter number 4, whatever we studied, as a one big question in semester, isn't it? So it will be a half an hour questions. Okay. I mean, if it is 2 hours for our full semester question, chapter 1 for half an hour, chapter 2 half an hour, 3 half an hour, 4 half an hour. So if I ask you to derive, or if I give you L, okay, so I'll show you the example later. But the thing is, you have to incorporate and find it. So only thing is you have to do is, as like I have explained you the heat equation, you have to find the answer for the same things. Okay, nothing new there. Okay, everything I have explained you very clearly here. Only thing is you have to refer how to solve one-dimensional wave equation. Okay, I'll give you wave equation can be written as da bar squared u over da bar x squared is equal to maybe okay, let me write this way. Maybe c squared. I'm using the same c squared. Okay, maybe depend on the wave equation for example, if I have a string. Okay, if we pull and leave it, it will be vibrate. No, it will be vibrate sometime. Or if I have, these things. No, in the physics also you may study it. If I have the string attached this point, if I pull and leave it, it will be vibrate like this. It is kind of a wave it created. Okay, also in the beach also you can see some waves. How it is can be real life situation we can model. Okay, that is you can refer how to model this. How to derive this equation. That is not for your course, but if you are interested, you can study. So one-dimensional wave equation will be this one. See the difference. One-dimensional heat equation I told you. Sorry, da bar u over da bar t and c squared da bar squared u over da bar x squared. Here only thing is this is also second order. That's all. Okay. So this also same process. There's nothing new. Okay. So there I told you we have got two ODE. Okay. Similarly here also both are second order now. So you will get something new. Same. Okay. You can refer in Google or any point, any books or anything. Okay. Only thing is you have to find the ux comma t. That's all. This is already dependent on x comma t. No. Okay. What is the wave equation solution by the separational variable? Okay. So that is your reference. Also, in our, so since of time consuming only, we are So these are your references. Okay, maybe in the exam we will have this. Don't expect whatever I explain. Okay, maybe whatever the reference question also may come. So you have to work on some way. Okay, so see here, in our separation of variable, heat equation, wave equation, Laplace equation. So boundary value problem I have explained you. Fourier series also I have explained. So what you do is same like heat equation, you have to solve wave equation as well as Laplace equation. Okay, and hopefully next lecture will be our last one. On that I will show you some example question. Okay, so that's all about our uh, lecture things. Okay, so be ready for before the next lecture. Please find the answer for the wave one dimensional wave equation as well as Laplace equation. So Laplace equation, no, what is the Laplace equation? Anyone? Laplace equation is not a big thing, I guess. Okay, it has some steps. So if I tell you, the thing is, uh, yeah. So Laplace equation in the sense you remember this one, no? Delta squared u is equal to 0 is our Laplace equation. So if I am only considering a one-dimensional case, it will be da by x squared is equal to 0. Sometimes they may ask you to find a second, two-dimensional, like uxx plus uyy, which is equal to 0. This is a two-dimensional case. Okay, so you can find a solution for this one, this kind of, okay, 2D Laplace equation using separation of variable. So you just put this heading and find the answers in the books or in any form of the way. Okay, so that's all about today's class. So I hope you have understood the way how we have derived our equation. It's not a big thing at all. Okay, what the thing is, you just have your ODE notes and just incorporate your answers here. Okay, only thing is we have some first order and second order, no? So you just refer those things and do here. Also in the notes, when you are doing, for example, x double dash plus lambda square x equal to 0, you do the ODE things, okay, here inside it. So it will be very understandable. Okay, so that's all about it, and I will find some question for you in the next lecture, and I will explain it. Okay, so since today is a Friday, I will finish now. So do you have any questions or anything? Please ask. Go through your notes. Have you written all the things? Okay, I think okay. Also in the notice, since yeah, heat equation, in the heat equation solution, we have had one boundary condition as like u 0 comma t is equal to 0, which is equal to u l comma t. Okay, and then one initial condition. Okay, but in the wave equation, since it has two second order one, they may give you some. Okay, analyze this boundary condition for this one, or as well as this also. U 0 comma t is equal to 0. Sorry, 1 one initial, boundary condition, but two initial condition. Okay, because we are going to solve two, no, I mean, da bar square d over da bar x square as well as da bar square d over da bar t square. There we also have to have two initial conditions. This may be like ux comma 0 is equal to f of x. Try this one also. Ut. Okay, ut means what? It is a space. Displacement. Yes, it is a space initial condition. Other one is a velocity. U of t mean what? Da bar u over da bar t. So rate of change of place, displacement will be velocity, no? So they may give you like this way, maybe gx. Okay, so try to solve this one. And if you have any doubts or anything, you can ask in the next lecture. Okay, please try to get all these answer, because I don't have time to explain everything because we need to end our coursework next week. But the references are yours. Okay, you have to work something. So we can have anything in the exam. So you have to be ready for anything. This question or this question or this question. Okay, that's your part. Okay, so I'll finish now. Okay, thank you very much.